Hey guys, in this video, instead of trying to explain how relational programming works, like how you can write relational programs or how a relational program language is implemented, I'll simply open up this repo session and go over some examples and try to run some of the relational programs and see what relational programming allows you to do. So hopefully after watching this video, you kind of get motivated and will look into the relevant literature on your own. The first example I want to show you is Peano numbers and the plus operation on those numbers. So here we have the definition of a Peano number. A natural number is defined as either z, which indicates 0, or as successor on that. So as you can see, it's a recursive definition. So for example, we have z, which is a natural number, and then we have, according to this second branch here, we have sz, a natural number as well. So here this z corresponds to 0 and this sc corresponds to 1. And similarly, we have SSC, which corresponds to 2. So I'm pretty sure many of you have if you've had your undergrad here at UMD, you have taken C30 and you've learned OCaml. So in OCaml, they usually just define the algebraic data type, which is recursive. But in Racket, people usually just use list because it's a dynamic language. So if you're not familiar with Peano number, you can just know what this thing represents by counting the number of s. And yeah, for example, here we have 2s, then it corresponds to the natural number 2. So here we're trying to define this plus operation. And here I wrote the definition of plus in the form which is more PL, I guess. So here we have this first rule which says plus 0 and any number n equals n itself. And the next rule is for the inductive case, which says plus the successor of m and n equals sp only if we have this recursive or this premise, recursive call or this premise, which is above the bar. So I guess from, if you're trying to implement this function or this plus operation in a functional language, you would read this thing backwards. So the thing to the right of the equality is the output. The thing to the right, the thing to the left is the input, which you should do a pattern matching on. So here we match if the first number is 0, and if so, we return n. Here we match if it's a non-zero number, and if so, we make this recursive call for plus mn, which gives us p, and then we use this result to produce the final output s of p. So here's the definition, which just as I explained, corresponds to these two rules that we have here. It allows you to calculate the sum of two Peano numbers. So we can try with some simple examples, like here we have 0 plus 0. The comment here is just to remind you what these things represent. We execute this function, and you see gives us back z, which is expected. And here we have 2 plus 1, and then we should see 3s on the output, and we do. So the implementation is probably correct, just testing by examples. So here's the more interesting program which is implemented in MiniKanren. So here we have this plus, which is functional, and here we have this plusso, which is relational. And by the way, this O at the end is pretty much a convention. People add an O whenever it's something relational, or more technically, it returns something that's a goal, which if you look into the implementation of MiniKanren, you'll better understand what's happening here. So you might wonder why it takes 3 arguments instead of just 2, because plus has 2 inputs and 1 output. The thing about MiniKanren is that it doesn't really discriminate the output. It treats inputs and output equally. So what this plus thing does, it generates a constraint which says, or I guess in MiniKanren term, it generates a goal which requires that m plus n equals p. This property must hold. And what is the property? This is what we're defining the body, which is the part I'm highlighting here. So if you look at the definition, it's actually very similar to the functional definition we have here, except instead of using pattern matching, we use this cond, which is similar to OR, as I noted in the comment here. So we have this first case where we check if m equals z, which corresponds to the first rule we have here. And then for the second case, we use this thing called fresh. So what fresh does is creating existential variables. It's actually the same as the exist, which you see from the thesis, I think. Yeah, they use exist. I mean, they're pretty much the same thing, but most of the modern MiniKanren implementations seem to use fresh instead of exist for whatever reason. So what this does, creates 2 fresh variables, and then we have this constraint which says m equals successor and some m minus 1. So this is very similar to what we have here. It simply says that m is a non-zero number. So instead of doing pattern matching, we use this equal to add a constraint. So MiniKanren knows that this is a non-zero number, and then we can do certain operations on it. And similarly, we state that p equals successor p minus 1. And here I'm kind of abusing the fact that in Racket you can use this dash in your variable names, but you can actually choose anything here. It doesn't really matter. And then we have this relation plus O, m minus 1, and p minus 1. So here we are kind of making a recursive call. Note how similar this is compared to this derivation we have here. So we are simply just making this recursive call to add these constraints to the environment. The word environment is something I made up, but you get what I mean. It's just making MiniKanren aware that there's this constraint. So I won't really get too much into detail of why this thing works, because I think it's better if you look at the implementation, try understanding on your own. But we can try some examples. Now, plus takes 3 arguments and returns a goal. And, well, a goal doesn't really give us much. So what we can do with a goal is we can run queries and find the possible things that satisfies the goal. For example, this thing, this form, which I'm including in the comment, it calls this run function and sends this query variable q, and then calls this plus function. So what this thing says in plain English is that it's asking if there exists a q such that it satisfies the property, the plus property, which we defined here. And so if plus mmp is a property that's true, then it means they satisfy this relation. That's how we define Plaso. So if we have this Plaso ZZQ, it's pretty much saying we're looking for some Q which satisfies this equation. Can you find it? And well, this is pretty much the same thing as the plus function, except we have to make this output explicit. And if we run it, we simply get Z, which is obvious because 0 plus 0 equals 0, and there's only a unique answer. This run star here, so for certain things, let's say something that's not deterministic, which can return multiple outputs, so MiniKanren will find multiple Qs that satisfies the property, in which case there's not only one result. So this run star returns all of those possible results, but here we know that there's only a single result, so run star just returns us one thing, not multiple. And if there is, it means our definition for plus is wrong, because plus is supposed to be a function. This whatever mn we have on the left-hand side, this question mark always has to be unique. Now, this really isn't very useful, because if you look at the number of lines for this relational program, it's actually a lot more than this functional program. And we don't have this concise syntax for pattern matching, and instead we have to spell out everything out. And yeah, it's pretty verbose, and people are lazy, so you can't expect people to write more code without a good reason to do so. So this next thing I'm going to show you is exactly the reason why relational programming can be extremely useful. So in this query above, we're asking if there's some Q which equals 0 plus 0, and it does exactly the same thing as the functional program does. But what if instead we ask something like this? Or, sorry, I should just return. So we're looking for a Q which equals to a pair of numbers, and this pair of numbers add up to 4. So this isn't something you can do in functional programs, because in functional programs you give 2 inputs, it gives you the output. But now you're asking, given this output, what are the possible inputs? And this is doable in MiniKanren. And as we'll see later, there's really no magic, which really is the coolest thing about MiniKanren, to be honest. If we run this query, actually here I'm doing the number 2 instead of 4. So let's try this again. This returns 0, 2, 1, 1, 2, 0. So yeah, exactly all possible combinations, which adds up to 2, which is great because we've finally done something which you can't easily do in a functional language. Another cool thing you can do is how you can define this minus operation in terms of plus operation, because of the property we've seen, or this functionality we've just observed, how we can run computations backwards. So normally this is how minus is defined. So if you have m minus n equals p, sometimes mathematicians just define it as if m minus n equals p, if and only if m equals n plus p. And we can encode this precisely in this one line. So m minus n equals p. It's the same as m plus p equals m. In some of the functional languages like Coq, people also use Peano number as an educational tool to teach people functional programming. And whenever it comes to implementing the minus function, people have to decide what to do when you're doing things like 0 minus 3, because if you're dealing with natural numbers, these things are not actually defined. So a common approach for those textbooks, they usually just take this special case. So if A is less than B, then the return value is always going to be 0, which seems quite arbitrary. But here, since we define this as a relation, and let's say we have this relation AB, and I guess just a quick math 101, a relation can be think of as a set of tuples or a set of pairs. And let's say if you have a set A and B, then A in B, B in B. If it's a function, then it requires that there's everything in A exists here and has to be unique. So a single A can correspond to multiple B's. But there's no such restriction for a relation. And for example, there's partial functions where not necessarily all A exists. We're not all elements from A were necessarily chosen. So in our case, minus is exactly a partial function, and if we try to subtract a positive number from something like 0, it will simply give us no result because it's not satisfiable. Like if you have 0 minus 4 equals, trying to look for something that equals this, and MiniKanren, that's how we defined it in terms of plus, to try to find a P which satisfies this plus condition, and that's how we define plus here. That's impossible. So I guess it's pretty elegant compared to functional language where to encode this partial functions you have to use optional types, which can get messy very quickly. And here let's just test this minus function we just defined. If we try to do 2 minus 1, we get back 1. And if we try to do 0 minus 1, there's no Q, which satisfies the equation, which is what one would normally expect. So that's all for Peano numbers. This reverse computing functionality doesn't seem very exciting because, it's just finding all the possible numbers that add up to a certain number which we've chosen. But this problem actually can get more interesting if we look at more involved functions. So for this part, I'm going to define an evaluator for the untyped lambda calculus. So here's this syntax for our lambda calculus, and here's the lambda abstraction, variable, and application. The reason why I'm using these this at var lambda is just for tagging it so I can easily discriminate between different cases. And here's some example terms. We have identity function, and we have the church encodings for true, false. Those are booleans, and then we have pairs, car, cooter. If you don't know, I think that's how we pronounce it, cooter, which is weird. And then we have cons, which is how you create a pair. Next, we have this relation, which describes the small step semantics for the untyped lambda calculus, the language which we just defined. The semantics I'm using here is called by name. That's the reduction strategy. So it's just to make things relatively easier to implement. Not that much. So if you look at its implementation, it's pretty simple. It checks if the expression is of the form E0, E1, an application, and if it is, then it can possibly be reduced. Then we split into another two cases. The case where E0 is already a lambda, then a single step means we just do the substitution. And if not, it means E0 can still be further reduced. So yeah, it's just taking a step from E0, 0. Then we use this compatibility rule, which sets ES, which is E taking a step, to E0 taking a step. This compatibility rule that I was talking about is different from the expressiveness paper's compatibility rule, if you're wondering if they're somehow connected. And after we define this single step function, we can define weak head normal form by repeatedly calling this step relation. And a weak head normal form, actually the definition can be non-trivial, but in this particular case, weak head normal form, a term is in weak head normal form if it is a lambda term. It is that simple. So in order to reduce it, we just first we check if it's already a lambda term, and if it is, we simply add this constraint which says the return value, E weak head normal form, is just the term itself. It's not doing anything. And if it's not a lambda term already, it tries to reduce it by using the step function. And if this step is successful, it calculates the weak head normal form of the expression that has taken one step. So I guess it's kind of similar to how you would write a functional program where the recursive calls are always happening on subterms. You usually want to do that, just make sure you are making progress. Though I guess it also help with termination if you're doing structural recursion, though obviously in this case there's no guarantee that this weak head normal form would terminate. Then we have this subtotal function, which I didn't actually mention, but we used it in this stepple function. It's simply doing variable substitution. Nothing interesting going on here, but it's probably the most lengthy function I've defined in this example. So it's separated into three cases, and I guess I can briefly go over it, but so we have this fresh, which introduces existential variables. Then this thing, you'll see this very often because it's pretty much pattern matching, but defined in a relational language. So you declare these two fresh variables, and you use these to restrict the shape of this term t, requiring it to be a lambda term. So if it's a lambda term and if we're performing substitution, we check if the binder is the same as the variable that we're substituting. And if that's the case, then if they're equal, then the body of the expression is being shadowed, so nothing happens. The substituted expression is the same as the original expression, which is what we're doing here. And if they're not equal, then we do substitution recursively on the body of the expression. It's very similar for application and the variable case. For application, you just recursively substitute for the two subterms. If you're applying E1, E0 to E1, you do substitution on both. And if it's a variable, well, you check if the variable is the same as the one you're replacing, and if so, you set the substitute expression to this E. Sorry. This E we have here. And otherwise, it just remains the same, because if the variables are different, then you shouldn't be substituting the values. So after implementing it, just like for the Peano number examples, we can run queries. So this query, since for this lambda calculus part I didn't include a functional example, it might get harder to explain, but this is pretty much an evaluator. So it's asking if I have this term, ID applied to ID, what is the thing that it reduces to? And if you're writing an evaluation function, calling the function on this term gives you whatever's here at the question mark. But again, here we are making everything explicit. So if we call the identity function, if we apply the identity function on the identity function itself, we should get back the same thing. And if you forgot how ID is defined, as you can see, it's exactly the same. It's just some sanity check to make sure our implementation is correct. And similarly, if we ID applied, we apply ID to Chu, we should get back the same church encoding of the term Chu. So that example is still pretty boring because this is something you could easily do in a functional programming language. So the next thing I'm going to show you, similar to the reverse computation for plus, we're going to do reverse computation for this weak-head normal form evaluator. So imagine what happens. Let's say we want to we give a set of constraints which says we have a function foo, and we want foo applied to 1, give us 1, foo applied to 2, give us 3, applied to 3, give us 5. If we get all these constraints, and then we make a query, and ask if these goals could be simultaneously satisfied. This looks familiar to some of you because this is exactly the problem of program synthesis by examples. So we're running a query asking if there's a certain function which satisfies all these properties or examples. So here I'm going to show you how we can take advantage of this reverse computation feature of relational programming to perform program synthesis. So just before we get into our example, let's define some church encoded terms. So here we have a pair of true and false, which in bracket is represented like this, pair of true and false. Similarly, we have false true, which in bracket just false true, looks like this. And then if we want to see our church, first let's see if our church encoding is correct or not. If we take the CUDA of the true and false pair, we should be getting back false. And you can see these two are the same. And similarly, if we take the CUDA of false true, the second element is true. So we should be getting back true, which we can confirm just typing it. These two are the same. So let's say we somehow forgot the church encoding for car of a pair. Then we can actually make a query to MiniKanren and figure out how, and ask MiniKanren to figure out how this car could be implemented. So instead of having this Q, which we've been using for representing the output, we just directly name our query variable as tcar. And here we are restricting the shape of tcar to be a lambda term because we know it takes a pair and returns something, where t, the fresh thing, is its body. Actually, this part is not quite necessary because it's going to figure out on its own that tcar has to be a lambda term, otherwise it can't take any steps. But the reason why I'm doing this is because I want to make sure that this p is named, because otherwise MiniKanren would give some very funky names to the variables. So this is restricting the shape of tcar, and then we have these two constraints. The first one says if we apply this function tcar, which we want to figure out how it's implemented, if it's applied to the pair of true and false, it gives us the first element. And if we apply this car to a pair of false and true, it gives us back false. And then again, you can see this WH and FO, the thing we defined above. So here you can see the advantage. Again, since it doesn't discriminate the output, you can have your output as given and leave some unknown in your input, in which case it's the tcar. So if you run this query, it's going to figure out some tcar which satisfies these two constraints, or these two examples. So we get like this function. Now, what does our car function actually looks like, which we define on our own? Looks like this, which is the same as what we have here. This is the one returned by MiniKanren itself as an attempt to synthesize it, and we can compare if they're the same. So this one is actually less obvious because it's using different variables. So we have lambda p, then we have this application. It's using x, y here, but it's actually alpha equivalent if we do a consistent renaming. Change p to x and x to y, then we get back the same thing. So yeah, you don't have to remember your church encoding anymore. Just remember to write down these examples and MiniKanren will be able to synthesize. Unfortunately, for our example, it's possible for MiniKanren to give you programs which are not closed, which are programs with or lambda expressions which contain free variables, but those things could be restricted if you add constraint. If you can add a closed constraint which ensures that the term contains no free variables. Yeah, then I guess the last example I'm going to show you is how you can recover your original functions just by using this define. So substo is defined as this relation where output is made explicit. So we know this substitution is deterministic. It returns a single result. So we can run the query. It's going to give us a singleton list. And we take the first element. Then the subst, it behaves the same as a function. It takes three things, returns an output. Though internally, we're using this run, making a query and supplying the output explicitly. I guess you can also write something called synthesis, which gives an output or a set of outputs, and it returns you a program which is able to produce the output given certain input. Similarly, we can apply the same changes to weak head normal form, define a function. So that's all for the examples. The next thing I want to show you is this paper, which I didn't ask you to read, but I think it's really crucial. It's actually very important to read this paper if you actually want to understand how MiniKanren works. So if you look at the title, it's actually MicroKanren. The paper was published in 2013, which you can see here, after the thesis. So there's been a lot of updates in terms of MiniKanren's implementation. To be honest, I found the implementation on this thesis pretty hard to read compared to this MicroKanren paper. If you don't trust me, just look at this last appendix. This 39 lines of code is the entire definition of MicroKanren, which isn't exactly MiniKanren, but it's like the core language, which has the same expressive power as MiniKanren. It's very easy to implement, and there's some tricks. For example, in MiniKanren, sometimes you write programs which doesn't terminate, and if you're able to go over these definitions, you can sort of see why you should order things in certain ways, or why you should put certain constraints before others in order for your program to terminate or run more efficiently. So if you look at the paper, you'll see that the implementation is actually pretty simple. It's not just the lines of code, but also the core idea. So the variables are simply wrapped with a vector. The reason for doing so is just because they don't want to use struct, which isn't really standard in Lisp or Scheme in general. And yeah, so this is how this equal is defined, which is pretty straightforward. So I guess the key idea here is that whenever we write down these things like equal, it's constructing goals, and the substitutions for that we end up getting, these are called states. So in this particular implementation on this paper, a state consists of a stream of substitutions. It's called a stream because it's not exactly a list. It could possibly be infinite, and it's also lazy in the sense that it doesn't calculate the result at once unless you request it. So, which is the reason why, let's say if we have something that returns that has 100 different inputs that produces a certain output, we're trying to use MiniKanren for synthesis, and you only want one of those, so you can use this run one query instead of run star, and it's able to actually speed it up because the stream isn't computed at once, and instead it only computes as much as you request. If you want one thing that satisfies the constraint, it will just compute that one particular output or that one particular program which satisfies the properties. If you're familiar with Haskell and you know a lot about list monad, that's pretty much all it's about, except the way you merge to a stream is by interleaving it instead of concatenating, because you want some sort of fairness, as you have to infinite list, and if you append it as usual, you will never be able to reach any element from the second list, which is why their implementation is slightly different. So I won't go too much into the details, but if you want, this paper is very helpful. Compared to this thesis, which defines the full MiniKanren language rather than from those tiny building blocks, I mean, it's obvious that this one is much easier to read, and it also helps you better understand the language itself. I guess that's it. Thank you.